Last time we stopped at our discussion at the bagging and ensemble learning. Today we're going to finish off the regularization strategy for deep learning with dropout and tangent drop prop. So here we go. First, let's start with dropout. Bagging involves training multiple models and evaluating them on each example. The problem with this approach is become impractical when each of the model is a large neural net, because training multiple hundreds of large neural net is very costly in terms of runtime and memory. So another technique called dropout provides an inexpensive approximation of training and evaluating bad ensemble of exponentially many neural net. That sounds very intriguing when you can train exponentially many neural networks. And the way it works is that dropout would train an ensemble of subnetworks that can be formed by removing non-output unit from an underlying base network. So I'll show you here the base network, which consists only 5 nodes, one of which is the output node. Now, from this base network, you can derive up to 16 subnetworks by just removing a combination of each of these 4 non-output nodes. So you can see here, you can keep the entire network, or you can remove X1, you can remove X2, you can remove H1, and so on and so forth. And so you have about 16 configuration of subnetwork. Well, you may notice that not all of these configuration will work because you need connection from the input all the way to the output, right? And some of the configuration, like this one and this one, among these doesn't have that connection. Now, keep in mind that as the number of nodes grow up, scale up, you don't see a lot of these unconnected network anymore, and you can have exponentially grow the number of possibility for subtasks. So the diversity of the subnetwork is vast. So what is some justification for doing dropout and how we actually accomplish dropout here? So at every training step, every neuron will have a probability of temporary dropout, which means ignore until the next step. This hyperparameter P is called the dropout rate, and typically P is set at 50%. And you can look at 1 minus P at the key probability. Now for a thought experiment, let's imagine that if you work at a company, but the company policy is the employee waking up in the morning, they can toss a fair coins, and then depend on how the coin land, head or tail, decided whether or not they go into work that day. Now, would the company perform better? It might be a strange thought experiment, but you can feel a few positive notes that the company would benefit from doing this. Well, it clearly benefit the employee for staying at home, but what about the company, right? So, well, the company will need to adapt this organization because now it cannot rely on any single person. It will adapt the way it works, the organized company, to accommodate for this task. The other one is that other employee will have a better strategy to cooperate with many co-workers, right? Because they cannot be relied on any single worker. They now have to cooperate with multiple co-workers. That sounds like a terrible idea for some of us. I know, just keep going. The nice thing also is one person quit, it doesn't make much of a difference with the organization of a companies, and the company become more independent of if someone quit, won't make much of a difference. So, well, it's unclear that would work for real company. No company ever trying to do that, but it certainly work for neural net. And the nice thing about this dropout is that it's also proposed no restriction or on the architecture of the network or the training method. And research show that dropout is more effective than the standard computationally inexpensive regularizer like weight decay or sparse constraint. So here I'm going to show you how using dropout when you propagate the signal forward, right? So start with this simple network that we see earlier. So what we're gonna do is that for each of these nodes, we're actually gonna expand it to be a sample vector mu associated with the input node or the hidden layer node. And basically what this vector does is, so this is a vector of length of all of the input and hidden units, okay? So here we would have a vector of 1, 2, 3, 4. 4, length of 4, because 4 hidden nodes and input nodes. So each of these associate with a node, and each of these are binary, and they sample independently from each other based on that dropout probability. So what happens if you draw this one 0, x1 will be discarded, right? So if you do think about this, like if this is a multiplication, if you multiply by 0, then this one will be discarded. Same with 1, if you draw 1 here, then you count x2 to be included in the network. So this is equivalent of you randomly selecting one of the subnetwork by just sample these mu vectors and then run back propagation just like you did at regular network. So this tends to be worked out that you can train exponentially number of subnetwork and then aggregate them, average them afterwards. So that seemed to work using this strategy. Now, the last strategy for regularization for deep learning that I want to discuss with you is what called tangent prop. And this one related to manifold learning. So we're going to do a bit of a review here. What is a manifold? So cursor dimensionality was a big problem in machine learning, and many machine learning algorithms try to overcome this cursor dimensionality by assuming that the data lies near a low dimensional manifold within a high dimensional space. And a definition for a manifold is that a d-dimensional manifold is a part of a n-dimensional space where d a lot less than n. And this manifold is locally resemble a d-dimensional hyperplane. Now that sounds pretty confusing, but if you think about it this way, think about how this layer look like a sheet and it wrap around like a Swiss roll, right? So this Swiss roll itself, because it's a sheet, it's a two-dimensional, but it lives in a three-dimensional space, right? So with locally, you can see this is according to a two-dimensional space, whereas overall it lives in a three-dimensional hyperspace, right? So this is an example. The Swiss roll is an example of 2D manifold that roll in the third dimension. Okay, I'm going to give you more example of real world in the manifold, especially in the image domain. So in the image domains, if you look at this bird flying image here, now the image have very high dimensionality. Think about the image of 1,000 by 1,000 pixel, have a total of 1 million pixels, so that you can see the number of dimension is per 1 million. But if you look at image in organized in such way, you realize that it's organized itself in a lot lower dimensionality, those manifold that live in that million dimension space. And for that, if you look at image in this way, organized this way, you can see if you go from top to bottom at this exit, this is mean just moving the bird or moving the camera closer to the bird, right? The bird's flying. And if you go this way, in this dimension, then it just recording different movement of the flapping of the wings. So this dimension meaning closer to the camera, and this dimension means the position of the wing. So it really, you can really compress this image into like two-dimensional manifold to generate this data. Now it's not quite that simple, but you can see that you can reduce down to that low-dimensional manifold. Another example for this would be this toy doll on a rotating base, and also the camera also have a rotating camera. And so if you again go up and down, it means that the camera are rotating the view angle, right? And if you go on this way, left to right, it means the base are rotating. And so that you get a series of these images by just alternating two factors. So this again is the two-dimensional manifold that live in a much, much higher dimensional space. So now that you get a quick idea of manifold, let's move on to talking about our algorithm or our regularizations. So we start with a tangent distant algorithms, and the tangent distant algorithm is a non-parametric nearest neighbor algorithm. And instead of using the Euclidean at the distant metric, it will use the distant metric derived from the knowledge of the manifold. And now one assumption we had to make here is that the example, the training example, that on the same manifold had to have come from the same class, had the same label, right? We had to make, otherwise you can't get beneficial from being a manifold, right? So same manifold means same class. So what happened is because we have the manifold live here, the classifier should be invariant for any variation, local variation that corresponding to the shape or to the moment of the manifold, right? So if you want to measure the nearest distance between two examples that live on two manifolds, then you can compute using the distance of those two manifolds, right? But because the manifolds shapes are very difficult to define, and sometimes you don't have a good way to derive this, so it's typically very difficult to compute this distance. Now another alternative is to approximate the manifold by its tangent plane, right? So if you imagine if you have some sort of transformation manifolds here, you can calculate a distance from the point that live on the manifold to a given point by approximating that distance for its tangent plane, and then calculate the distance from the tangent plane to that point, right? And this tangent to a point can be solved by just solving a linear system, right? So how's that benefit our regularization, right? So tangent prop algorithms derived from the tangent distance train a neural net classifier with an extra penalty or the regularizer to make each output fx of the neural net locally invariant to unknown factors of variation, right? So that's a mouthful, but let's see what it means. So locally invariant, it can be achieved by requiring the gradient with respect to x of the output fx to be orthogonal to a known manifold tangent vector. So we're going to find the manifold tangent vector v at x. And the way we do that, we're going to add some regularization penalty, right? And the regularization penalty is just the, we want to make this gradient dot product with the vector v square to be small. And what does that mean? That means that the directional derivative of f at x in the direction of v should be small, right? And let me explain why is this significant, right? Why is it direction v should be small? Because when you move f from x in the direction of v, you actually move very close to the shape of the manifold at x. Locally, it should be very similar. And so when you move the f along the tangent direction, the change should be small because you stay within the manifold. So you assume that all the class there, a sample there have the same class. So you want to make sure that directional derivative is small. Now, on the other word, if you move off the tangent, right, you move on the normal direction of the tangent, then you expect that the directional derivative should be large because you're moving away from the manifold, right? So in the next slide, I will show you in the graphic. Hopefully, that will get you better. But that is how you can explain why using this term, this dot product for the regularization and expect this to be small. Right? So for most neural net, it will sum over many output instead of just fx. But for simplicity, we just use one output here. And you may ask, how do I find the tangent vector v? And typically, there is an entire field dedicated to find the tangent vector v called manifold learning. But typically, we will treat the tangent vector v at a priori from the formal knowledge of the effects of transformation. So you see those images that you see earlier could be due to some translation, rotation of the object in the image, or the scaling of the image, when you move the bird in and out closer to the camera. So if you know those effects of transformation at a priori, then you can determine the tangent vector v. Right? So we're not trying to find v analytically, but rather that come at a priori. And finally, tangent prop actually used a lot in not just in supervised learning, but also in reinforcement learning. Okay, so let me illustrate how it actually works. So each of these lines represent a separate manifold, which is a 2D manifold live in a 1D manifold, which is the line here, that live in a 2D plane. And we expect that the classification change rapidly if it moves in the normal vector, which is this vector, normal to the tangent, right? So if the classifier function move in this direction, it should change very fast because you are about to go to become another class. However, if you move in the direction of the tangent, like this direction or that direction, then you expect the direction that it won't. The classification result won't change as much because you assume that with the tangent line, you move very closely to the manifold. And if you move closely to a manifold, your output shouldn't change very much. Right? So that basically the gist of it. Tangent prop regulate fx not to change when x move along with the manifold. Right? So this is a pretty advanced method, and it's done truly in research, and people had used it, but it's very close relation to, guess what, dataset augmentation that we covered earlier, and in the way that both of them are closely related because the user can encode the knowledge of the task by specifying that set of transformation that would not alter the output of the network, right? Remember the one that we translate the mushroom image, and then we zoom in and we brighten it up, or we cropped it, or we rotate it. All this transformation will not change the output of the image in terms of data transformation. Same with the manifold tangent prop method. Now the difference is that in dataset segmentation, the network is trained to correct distinct input created by that transformation, whereas the tangent prop do not require explicitly to visit the new input point. Rather, it regulates the model to resist the change or the perturbation in the direction that correspond to the specified transformation or the shape of the manifold. Augmentation have resistance to larger perturbation than tangent prop because with the tangent of manifold, it should be done on a very local variation, whereas the augmentation you can change the input image very drastically, right? Like rotate it 180 degrees or something, without changing the output of the training image. So the bottom lines here, I guess, is that tangent prop is very intellectually elegant with the manifold, but the augmentation, dataset augmentation, might work better in practice. So it depends on the problem here, of course. So we had just surveyed 7 general strategy to regularize the neural network. Number 1, parameter norm with L2 and L1. Dataset augmentation, when you get to manipulate the input of the data. Multitask learning or parameter sharing. Early stopping, very popular method. Backing and ensample learning method. Dropout. And finally, tangent prop. These certainly is just the beginning discussion, and neural net with regularization typically perform better an unobserved data set. And certainly, this is a central theme of machine learning, and we will revisit them periodically in the course. So, this is it for regularization. On the next module, we'll cover optimizations of deep network. Until then, take care.